Okay, 3.28 is a pretty simple exercise that's just sort of reinforcing this idea that we introduced earlier in the chapter, that when you run into functions of operators, you can treat the operator as if it were a variable when it comes to the context of expanding the function itself into a Taylor series. So we're going to say, okay, suppose that we have a function d by dx, which is the derivative operator. We want to find the following formulas. So part A, sine of d hat applied onto x to the power of 5. So if I'm going to treat this like a function of a variable and Taylor expand it, well, sine of d hat can be expanded into a Taylor series as d hat minus d hat cubed over 3 factorial plus d hat to the fifth over fifth factorial, and so on and so on. It's not going to matter anymore after the fifth term because at d to the power of 5 I have a fifth derivative, and this is only x to the power of 5. So if I'm applying this whole thing onto x to the power of 5, I'm going to get d by dx to the power of x to the power of 5 minus 1 over 6 times d cubed by dx cubed of x to the power of 5 plus 1 over, let's see, that's 20 times 6, so that's like 120. Right? It's going to be 120. And then d to the fifth of dx to the fifth of x to the power of 5. This is going to give me something like 5x to the fourth minus, let's see, 5x to the fourth goes to 20x cubed, right? This is d1, this is d2, d3 is going to be like 60x to the squared, right? So take the 6 at the bottom, that's 10x squared, plus, and then this is d5, so d5, it's just, doing it again, so that's 120x for d4, and then just 120 for d5, so 120 over 120, that's 1, so just plus 1, and this is the answer for part A. Okay. Now, let's move on to part B, which is this term. So now you have a 1 over 1 minus d hat over 2 applied onto cosine of x. So obviously, this term right here is taking on the form of something like 1 over 1 minus x, right? And assuming that you're following the radius convergence and x has a magnitude that's less than 1, or less than or equal to 1, this is going to give you a summation in the form of a Taylor series of n equals 0 of x to the power of n, right? So if your x is d hat over 2, this is going to give you a summation for n equals 0 of 1/2 to the power of n, like that, and then d hat to the n. So this is like, 1 plus 1/2 d by dx plus 1/4 d2 by dx squared plus 1/8 d3 by d cubed squared, and so on and so on. If I'm applying that onto cosine of x, so if this entire thing is being multiplied by cosine of x at the front, this will give me something like cosine of x plus, or I guess minus 1/2 sine of x, minus 1/4 cosine x plus 1/8 sine x, plus 1/16 cosine x. I'm just writing this out fully because it looks like there's a pattern, right? Minus 132 sine x plus, or minus 164 cosine x, so on and so on and so on and so on. So what this looks like to me is that I have two different series. I have a cosine series and I have a sine series. So I have like a cosine x minus 1/4 cosine x plus 1 over 16 cosine x minus 1 over 64 cosine x, and so on and so on and so on. And then on the other hand, I have a sine form, which is like negative 1/2 sine x plus 1/8 sine x minus 1 over 32 sine x, and so on and so on. And you know what, let's just go up to 64 just because this is going to be plus, well actually it's not going to go up to 64, so I'm just going to leave it like that, so on and so on. So I have really two series. This is series 1 and this is series 2, one in terms of cosine, one in terms of sine. I can try and condense these down into actual summations. So the first thing I'm going to do is I'm going to get rid of the cosine, because I can substitute that out, right? And it's going to be 1 minus 1/4 plus 1 over 16 minus 1 over 64, so on, so on, so on. And on the other hand, over here I have a sine of x, and then negative 1/2 plus 1/8 minus 1 over 32, and so on and so on and so on, right? So let's see. Obviously there's a negative 1 in sort of the formula for the summation, right? So this is going to be cosine x summation, and let's see. I'm going to start from n equals 0 because it looks like we start with a 1. So this looks to me something like 2 squared n, right? Because that's 0. And then at 1, that's 2 squared, that's 4. At 2, that's 2 to the 4th, which is 16. 2, 4, 8, 16, right? And then at n equals 3, it's 2 to the power of 6, which is 64. Yeah, so that's the bottom. And at the top, because I'm alternating signs from positive, negative, it's a negative 1 to the power of n, right? So that way it's positive, and then negative, and then positive, negative, and so on and so on. Yeah, that seems right to me. So that's your first series. Now on the bottom here, this second series, sine of x, n equals 0, same thing. So once again, right, I have sort of a negative, positive thing, but this is the opposite direction. So it might be, I add a negative at the front and then negative 1 to the power of n, right? So that way it's first term is 0, n equals 1, which is my first non-zero term. Or I guess at n equals 0, I have positive 1, which becomes a negative. And at n equals 1, I have a negative, which becomes positive. So negative, positive. I've reversed the order of the negative positives by adding a negative at the front. At the bottom, this is a little bit weirder. Let's see. So, well, actually, no. It looks like I'm just dividing for every term here, it looks like the corresponding term here is divided by half. So I can do the same thing. I do 2 to the power of 2n, and I can just divide everything here by 2, right? And in that case, I think this term is correct. Negative 1. Yeah, that looks right to me. So in that case, that's my second series. So in reality, right, this thing is ultimately going to simplify down. Let me copy it over. This is also ultimately going to equal the sum of two series. So cosine of x, summation n equals 0 of negative 1 to the power of n, and then 2 to the power of 2n. And I'm going to subtract by sine of x over 2, summation of the same thing, negative 1 to the power of n over 2 to the power of 2n, right? And at this point, what you're looking at here is now two geometric series, right? This is a geometric series. And we know that for a geometric, or maybe you don't know, but just as a quick refresher, if you're dealing with a geometric series, it converges, so long as your multiplying factor is less than magnitude 1, it converges ultimately to a formula of a over 1 minus r, right? Where a is the constant at the front of the series, and then r is the multiplicative factor. In this case, your multiplicative factor is just the entire summation term, right? It's just r, in this case, is equal to, this is like negative 1 over 4, because it's 2 squared, right? And then a is just equal to like either cosine of x or sine of x, but if I'm just looking at the summation itself, a is just equal to 1, right? So ultimately, this summation thing is going to equal 1 over 1 minus negative 1/4, which is going to be equal to 1 over 1 plus 1/4, which is equal to 1 over 5 over 4, which is equal to 4 over 5. So if I plug this in for everything, then I'm going to get cosine of x times 4/5 minus sine of x over 2 times 4/5. This becomes a 2 at the top, so I'm left with 4 over 5 cosine x minus 2 over 5 sine x, and that's the end of this problem.